So, as I said, we need to multiply times multiply the energy density per unit area by the group velocity. So, the group velocity can be estimated through the relationship that you see there. I'm not sure whether you already saw it with Professor Archetti. Basically, you can estimate it as the product between G and C depth to the power of 1.5. So square root of G times C depth. And it can also be expressed in some textbooks, as you see on the extreme right-hand side, as the product of G times HB, which is again wave height, divided by K, where K is the breaker index, defined as the ratio between HB, wave height, and BB, water depth. And this is again, I don't really need that you remember the expression for the group velocity. This is something that I guess that you already know. And if I'm just showing it because if you don't know it, it's it's better if you know. At least in terms of terminology and in terms of effective variables to determine the group velocity. Let's say that, again, I don't really need that you learn by memory this. So in the development of the CERC formula, there are some steps that you can skip, and I will tell you what are the steps that you can skip. And this is something that you have to learn by memory, so it's the first one that I suggest you to skip. The only thing, just remember what is group velocity. Okay, and then here there is another step that is a bit complicated. So basically, what did we derive so far? We derived the energy flux through a unit width in the transversal direction of the wave. That's fine. But then we have to consider the wave direction, because the energy flux is independent of the wave direction. And what can be the extreme range, what are the extremes of the range of the wave direction? One extreme is wave perpendicular to the coastline, and the other extreme is wave parallel to the coastline. You understand that the first extreme we already excluded it because we are talking about a long-short sediment transport. So we are implicitly excluding the case in which the wave is perpendicular. Also, we are de facto excluding also the case where the wave is parallel to the coastline, because it doesn't happen really. It may happen that waves are almost parallel to the coastline, but especially if the coastline changes its direction. But you know that usually waves tend to approach the coastline at an angle for the effect of refraction. So this is the situation where a wave is indefinitely traveling parallel to the coastline is almost impossible unless you have a case which is not the case of the beach, where you have a seawall. If you have a seawall or the coast that behaves like a wall, it may happen that you see for a long direction waves traveling in the parallel direction, even if you have some bending, even if there is a wall, because you understand friction causes the bending of the wave, causes refraction. If we talk about beaches, this is a case that it's not possible, but it may be if the coastline changes its direction, that for a limited amount of traveling distance, you may have a situation where the wave is close to parallel. In between, you have several different situations. And then, of course, we have to take into account the direction of waves, because if the wave is perpendicular to the coastline, we don't have cross-short sediment transport. So we have to introduce a multiplier that takes into account the angle. And the first multiplier is a multiplier that should annihilate, should bring to zero the amount of sediment transport if the wave is crossing the coastline, is perpendicular. So the easiest way to introduce such a multiplier is to introduce a sin function. First of all, we have to define the angle, as I said before. So let's take the convention that let me see, because here it's not defined. I think it is the acute angle, but let me read it because okay. Okay. Let's introduce angle alpha. Let me make a sketch. And let's see whether the sketch that I'm making is consistent. So we try to develop it together. So we have the coastline here. And we have the wave direction here. Okay. Sorry. So alpha is defined as the acute angle between the breaker line and the coastline. Okay. The breaker line is this one. This is the breaker line. It's perpendicular to the wave direction by definition of plane wave. And then you see that the breaker line with the coastline identifies two angles. Let's take the acute, I'm not sure the pronunciation is correct, alpha E. It is displayed on the screen with a different character because alpha I was not able in HTML language to display alpha, or maybe that I didn't study enough, but anyway, let's take into account that it's displayed in with a different character, but this is an alpha. Okay, so this angle is equal to, basically you see that as the wave approaches the perpendicular direction to the coastline, alpha goes to 0. Okay, so if I change basically and I bring the wave perpendicular, so I put the breaker line, the red line, I make it more, let me say, more parallel to the coastline, alpha tends to 0. So what's reasonable to do is to introduce the multiplier as sin alpha. Sin alpha. Okay, so if let me indicate with PL the segment, the rate of segment transport in weight. Okay, so I get it by multiplying EBW times sin alpha. This takes into account the fact that when the wave is approaching the coastline perpendicularly, I don't have any along short segment transport. So when alpha becomes close to 0, the segment transport are delayed. Let's forget about this part here, okay? Okay, good. What is ABB is, again, flux of energy. Okay, EB is energy per unit density. By multiplying it times the group velocity, we get EBV. Okay, sin alpha to take into account what I just said. And now your question should be, why do I multiply also times cos alpha? Good question. So what happens if alpha becomes 90 degrees? The wave is traveling along a direction that is parallel to the coastline. So you may say, and then, so what? I mean, what's the problem? The problem is that if you think in terms of braking, effectiveness of braking waves, wave tends to brake especially if they approach the coastline perpendicularly. If the angle of waves is not perpendicular, becomes closer, the wave becomes closer to parallel, you don't see much breaking. Look at the beaches, how they behave when there are waves. You have a very strong breaking with a lot of turbulence if waves approach the coastline perpendicularly. If the waves approach the coast at an angle, you see that the breaking, okay, you still see breaking, but not so much turbulent. Why is that? Because breaking is originated by the friction of the waves against the sea bottom. If the wave travels parallel to the coastline, they have only a small part of friction. They basically get in touch with the sea bottom only in the part of the wave that is close to the coast. But the other part of the wave, as the waves get far from the coast, doesn't break because there is no friction against the sea bottom. And therefore, we need to introduce a multiplier taking into account that in the extreme case, impossible case, in which alpha is 90 degrees, sediment transport is 0. And this is why we put cos alpha here. Interesting. And if you accept this, because this is, of course, it's a formulation that it's subjective. The fact that we introduce this multiplier, sin alpha, cos alpha, it's not dictated by a physical law. It's just the fact that we want to say, okay, I want to have the max of breaking, I want to take into account that I have the max of breaking when alpha is 0, but in this case, I don't have an optional sediment transport. And the fact that I assume that the relationship, this dependence of sediment transport on the angle, the approaching angle of the wave, the fact that I assume that this dependence is dictated by a sin function and a cos function is subjective. Okay? So keep into account that it's an interesting idea, but still it's something that is not physically based. But it's interesting, and if we accept this description, it means that the worst case is alpha equal to 45 degrees. This is the worst case. So, for the same wave energy flux, you have more sediment transport if you approach the coastline at an angle defined in this way of 45 degrees. Okay, fine. But we introduced here something that is not really physical, and therefore what I would say is, okay, let's do that, but let's introduce an empirical parameter. So this representation here, that's fine, I mean, but what is it saying? It says that sediment transport rate in terms of weight is equal to the product of energy flux times energy flux, which is HPV, times sin alpha cos alpha. And so the famous lamp that we talked about, the uncertainty lamp, should turn on in your mind like, okay, but this is something that is subjective. It's something that it's affected by uncertainty. And therefore, the ideal conclusion in this case is I should introduce a coefficient here. A parameter. What is a parameter? A parameter, when we talk about a relationship, an analytical relationship, what is a parameter? A parameter, there is no clear definition for a parameter, but let me provide an example first. So linear regression, straight line, y is equal to a times a plus b times x. This is a straight line, okay? And there is no doubt that if a and b are constant, this is an equation of a straight line in terms of y-x relationship. But you have A and B, and what happens if they change? It remains a straight line, but we can change the slope, B, and we can change the position of the straight line through A. So these are two parameters. They don't change the structure of this relationship. It's still a straight line, but they make it flexible. So, if I say y equal x, this is not a flexible relationship. It's just something like that. If I change A and B, okay, it can become like that, several possibilities, still a straight line. So this is the definition of parameters. These are coefficient of an equation, a possible definition. This is the definition that I like. Coefficient in an analytical equation, analytical relationship, which don't change the structure of the equation, but make it more flexible. Flexibility. And therefore, I think we need to introduce a parameter here to make it flexible, to take into account uncertainty. So let's look at the next step. First of all, okay, we discussed about it. First of all, this is just a simple transformation by a simple use of trigonometric functions. We can prove that sin alpha cos alpha is equal to sin 2 alpha 1/2. And just check it, and we cannot lose time in making the demonstration proofs of trigonometric relationship. It's true, I tell you. And then you see that I introduce the multiplier k. And by also using another symbol, which I call IL. What is IL? It's the immersed meaning, you know, that if a sediment is immersed, it has a different weight with respect to the dry situation. So let me introduce here the immersed and actual. Actual means that it's more consistent, it's more close to reality. Weight transport rate by multiplying simply PL by a constant K. It's an empirical coefficient. It is introduced to take into account uncertainty, to take into account the fact that we made assumptions. The first assumption is sediment weight proportional to energy flux. The second assumption was sin alpha cos alpha, whatever. So let's introduce K. And K is a dimensionless parameter. It's between 0 and 1. It's between 0 and 1 because, you know, experience shows that actually, in many cases, K is equal to 0.7. So if you don't know what is K, an ideal value, just take 0.7. And because it turns out from several experiments in the lab and in the field that K is equal to 0.7. Or let's say it's close to 0.7. And let me say something about field experiments that can be also lab experiments. When you introduce empirical coefficients or when you want to derive empirical relationships, usually, as I said, you use observations to derive them. And these observations can be done in the field. It's open lab, it's also called, meaning that you go over a beach and you take measurements by taking into account that any beach is just an example, a single example, and any beach has its own behavior. So ideally, if you make an experiment in an open lab, you should repeat the same experiment in several different beaches and then see if there is some regularity, or see if you can explain variability, in this case K, based on beaches' behavior. An alternative, which is easier easier is to make the experiments in the lab. The lab is an ideal situation, so you have to keep into account that it's not representative of the real situation, strictly speaking. On the other hand, the lab is more controlled, is completely controlled. So it gives to you an information that is really complementary to what you get in the field. So there are some people who say, some engineers who say, I don't like the lab experiments, ideally you should go in the field. Other people say, yeah, in the field there is too much uncertainty, I prefer the lab. They are complementary. I mean, in the lab you can control everything. It's extremely important to make lab experiments. And unfortunately, given the shortage of economic resources today, you know, lab experiments, open lab or closed indoor labs, they are decreasing. Even if I think about thesis for the students, there are less resources today for dedicating time and resources, again, to making lab experiments. Also, you have to take into account, just to provide information that is not relevant to what I'm saying, but you have to take into account that today, in the past, when a student developed a master degree thesis, it was quite common to stay busy for, say, 6, 8 months. And today it's different because you know that the calendar of your studies is more rigid, is more defined. And this is also why it's difficult to involve students in lab experiments. But there is also the reason of the economic resources. We have less technicians in the labs, we have less money for supporting the experiments. Anyway, whatever experiment you make in an indoor lab or open lab, it's desirable that you make a lot of observations, and in this case, suggested value for k is 0.7. So, basically we are at the point where, by knowing the behavior of waves and knowing whatever is relevant to the beach, k value, we can compute the sediment rate in terms of immersed weight. Now, you may be interested in the volume of sediments. It's more interesting. And you can easily understand that from a rate in weight, you can derive the rate in volume. What you need is to know the mass density of the sediments. Of course, if you want to pass from weight to volume, you need mass density, but you need some more than mass density, because this is a porous media. Sediments are porous media, which means that you need to also know porosity, because the higher the porosity, and the porosity is defined as, let me use the symbol, I'm not sure whether I used E. Oh, okay, let me check, because I think that it is the last part of the lecture that is not. The porosity I'm using here, N. So, I'm sorry, I need to focus on this equation. Here, the porosity is N. So, if you have a porous media, how is porosity defined? Very trivial. Porosity is given by the volume of voids divided by the total volume of the sediments. So, of course, porosity is varying from 0 and 1. Porosity 1 means that the volume is completely occupied by voids, so let me remove the equal sign here, because otherwise it's not a porous media. And we can remove also the equal sign also from here, because porosity 0 means that you have no voids, so it's not a porous media. But it's clear that the larger the porosity, the larger the volume for the same weight of sediments. Okay? Because we are talking about weight of sediments, and of course the larger the porosity, the larger the volume for the same weight. So in order to get the volume sediment transport rate, you have to take, of course, the product between P, L, and K, and to divide it by what you see in the right part of the equation that takes into account mass density times G, which is the weight, the specific weight. The specific weight of the sediment is given by the product of mass density times acceleration of gravity, and then porosity. And you see that for increasing porosity, if porosity gets close to 1, you have the volume of the sediment that increases, which is what we are expecting. I think it is useful if you try to remember this equation because it can be easily derived. I'm not deriving it because it's trivial, and it can be easily derived. So if you remember it, I think it is useful. And this is our final target. Okay? We know the sediment transport rate in terms of weight and in terms of volume. We are mainly interested in volume because what is shaping the beach is the volume of sediments, not really the weight. So this is actually our final target. Okay. Now, the next question is, okay, perfect. I can compute the sediment transport rate. I can compute Q, I call it Qn. The volumetric sediment transport rate, okay? Perfect. But this is just, it's not my design variable, this is an input of my design project. And keep in mind, this is something that I assume to be a kind of constant. So straight coastline, waves that are approaching the coast with the same angle, same type of sediments, so same porosity, same everything. But actually, what happens in the real cases, it's a bit different. What happens in the real cases is that you have a coastline that behaves like this. And okay, let's assume that the waves are approaching the coast at the same angle. Actually, it's not like that, you know this. It's not like that because if you have this wave direction from offshore, you know that there is a refraction, so the wave angle is not really the same. But I mean, it is a good approximation in many cases to assume that the wave angle is unchanged. But for sure, it's not a good approximation if you assimilate the coastline to a straight line. So this computation in the real cases cannot be a computation that is extended over a long distance. This must be part of a discrete computation for assigned spatial steps. What I mean is that, okay, you may assume that you treat this coast part of coastline as a unique spatial step because the angle doesn't change much. The angle alpha b doesn't change much. But then if you move here, and this direction in which I am discretizing is just an arbitrary direction, and usually we take a discretization along an assigned direction which is close to the average perpendicular to the coastline. Okay? But in this case, in this spatial step, you have a different angle. So you need to compute a different, make a different computation. And then you have another spatial step. Here again, different angle, another here. So what we do usually is to move along the coastline through delta, let's call it x. Let's call indicating x the abscissa along the coast, the average coastline. Okay? So we move through delta x, And for each delta x, we compute an onshore sediment transport. So what happens is that you end up with this one, and let's assume that the length of the arrow is proportional to the volume of what comes out. It's proportional to the volume, the sediment transport rate in terms of volume, okay? And then we go here. Here, you see that the waves are a bit parallel to the coastline. So, I expect that here I have a shorter arrow. Okay? Okay, and then here, maybe the arrow is a bit longer. And then here, maybe like that. So basically for each delta x, you compute a sediment transport rate, and it may happen that here you have a big rate, meaning that the waves are eroding quite a lot. Here, the waves don't erode much. And therefore, if they don't erode much, it means that they have less energy to erode. And therefore, here you have accretion, because you have deposition of sediment. Accretion means in a zone where the beach is growing, is extending, is collecting sediments. So here you may have erosion here, accretion here, and then here may be stable, because it's the same sediment transport rate, and here you have erosion again, and then maybe accretion here. So what you see indeed with this kind of approach is displacement of sediments, which is what actually occurs, displacement. Keep in mind that there is an underlying assumption that I never mentioned, and it's mentioned in the web pages. The underlying assumption is that you have enough sediments, always. Meaning that if you have an increase in energy, you have indeed also available sediments to be mobilized. It may happen that you won't have sediments, and therefore this is to be taken into account. It may happen that you have a protection somewhere. So let's suppose that here you end up with erosion, but there might be a seawall. If there is a seawall, of course you have to intervene and put zero here. And then, if you don't have erosion here, it means that here you don't have accretion, because there are no sediments entering into here. And therefore you have erosion here. And this is what actually happens. If you protect a part of the beach, you transfer erosion downwind. Downwind is here, what it means. Okay. Downwind means that you are moving along the coast by following the direction of the wind. Upwind is if you go against wind. Okay? So when you, again, build a protection structure for a beach, indeed, what happens is that you transfer erosion downwind, which is fine, it's coherent with the reasoning that I was making. I was developing with you. So we have to use, we can use this kind of approach to study how the beach evolves. And then let's suppose that, let's go back, or let's focus here. Oh, this is stable. Let's focus here, erosion. So here we have erosion, and we can estimate the volume of sediments that is eroded. It's the difference between this transport entering into this spatial stack and the transport in the spatial stack. So if you have a difference, meaning that you have more transport capacity than sediment in flow, there is erosion. And then the next question is, how does the beach evolves? Of course, the beach moves landward. So there is when there is erosion, there is a movement of the beach landward. But how this movement occurs? If you have accretion, you have a movement of the beach seaward. But again, same question. How this movement occurs? researchers tried to develop models to explain these processes. How the pitch evolves. Intuitively, if you try to guess, what may you conclude? Okay, let's focus again on this spatial step. We have erosion. So you have some sediment coming in, but there is a lot of energy. And therefore, what I may expect is, if, let's suppose that I don't have any sediments inflowing. If you don't have any sediments inflowing, what happens is that, like here, you don't have any sediment inflowing because you protect this part of the beach. And then, what happens here is that suddenly, waves with a lot of energy get in touch with an erodible coast. What happens is that they start eroding soon. But as they start eroding, they basically upload sediments, and therefore the eroding capacity decreases. So, I mean, the development of this process is not taking place with the same behaviors along the whole time step. You have to understand that when there is a lot of energy and no sediment transport, there is a very high eroding capacity. When, conversely, the wave starts uploading sediments, then the eroding capacity decreases. Because the energy is the same, but the waves, while it erodes, it's also releasing sediments. The same thing, if you have a big flux of sediments entering into a quiet zone, what happens is that as soon as they get in, they start settling down, and then asymptotically, the content of sediments of the wave goes to zero. So you have high deposition at the beginning, just at the entrance, and then asymptotically it goes to zero. So people try to understand these processes, and they formulated models with different level of complexity. The model